Hello, welcome back to Econometrics YouTube channel. So, my name is Ololi Godwin, obviously. We'll be talking about the Asian in this particular class. It's a series of classes. I think we should be having two or three, two, three classes. It depends. Okay, so this topic is just an extension of matrices. Okay, what we learned in matrices and so on and so forth. So what we'll be talking about in matrices is the application of we're looking at the application of Cramer's rule, and then from there we're extending to testing if the function, whatever function we have, if it is optimized. That is it minimized, is it maximized? All right. So today's topic is the Asian. So where we are going to really is the bordered Asian constrained optimization. But the thing is that the rule that applies to Asian here is the same rule that applies to the bordered Asian constrained optimization. When you're doing optimization problems in economics. All right. So if you know these things, if you know what I'm going to talk about in this class and the one in the next class, I think you should be able to handle constraint optimization using bordered Asian approach. At the end of the day. So the Asian is basically a simplified approach of ascertaining if a function is optimized. All right, it's just a no, it's just a simplified way of knowing if your maybe cost function now, if your cost function is minimized. All right, normally your cost function should be minimized. Okay, you don't maximize costs. Right, how about profit? You maximize profit. It's a positive thing. It's a good thing. Okay, how about sales? You maximize sales. All of those things. So the Asian is just another way of helping us to know if our functions are at minimum or at a maximum, and it's kind of simple. I kind of like it. Now, the one that we've been used to, the kind of optimization that we've been doing, that we've been used to, for you to be, watching this video, you should be in your third year. At least this should be from your third year. All right. So before this particular time, um, or this should be in your third year, upwards. So before this particular time, you must have done partial differentiation, and you optimizing multivariate functions. That is functions with more than one independent variables. So there is a rule that we use, when you have multivariate functions. So and that is what we have here. First thing is that your first order condition, whether zx or zy, when you differentiate a function z with respect to x, all right, is equal to zy, then we make it equal to 0. So that's the first order condition. Okay, then that's not kind of concrete yet. So we have to look at the second order condition or other, maybe not just second order, they just other conditions that have to be met for us to be able to say if our function is minimized or maximized. So here when you say zx equals zy equals 0, what we're trying to get are your critical values or your turning point. So here, so zxx, zyy, like these two things. So zxx, zyy, are they greater than 0? If they are greater than 0, then that's an indication that your critical values, at your critical values, your function is at a minimum point. Your function is minimized, but you're not so sure. All right, until you verify this. So is your zxx multiplied by zyy, is it greater than your zxy squared? All right. So if you have this where your zxx is greater than 0, your zyy is greater than 0, and this condition is also holding, so that means your function is at a minimum, you know, at the critical point that you derived or that you obtained. Now, there's the other one is if your zxx is lesser than 0, that is, if it is negative, and your zyy is the same, it's negative as well. So your function is an indication that your function is at a maximum point, at the critical values that you got. But you are not so sure until this other condition holds. So your zxx multiplied by your zyy is greater than your zxy squared. So I'm not going into detail here because ordinarily I think you should know what these things mean. Okay, so where is that xy equals zyx? Yeah, normally you should know that by now. All right, so we have the border. No, we have the Asian, so written in matrix format. I said we are going to be treating an example, and you would see that after looking for your partial derivatives, you are going to be having matrix. You'll be having your solution in a matrix format, formats, and from there you kind of you have to like solve as your critical values and test whatever they are. So you have your Asian. So we have H, right? So it's like more or less like this H. You have H equals to zxx, zxy beside it, zyx, zyy. So here, this you call this your second order direct partials. So zxx and zyy, they're second order direct partial. That is, uh, this is you differentiating two times. So zx the first, then zxx, that's the second time. So you call them direct because you're differentiating with respect to a particular variable, independent variable. So the variable here is x. So you're differentiating x, you're differentiating z with respect to x. You're differentiating that answer with respect to x again. So we call it a second order direct, partials. All right. So the same thing with ZYY. Okay, then you have ZYX and ZXY. So these are second order, but instead of being direct partials, they are cross partials. Okay, because first you differentiate Z with respect to X, then you differentiate X with respect to Y. So it's like a cross, you are crossing it. So you have ZXY, then you have ZYX here. So it's not so difficult to memorize. This is ZXX, the other one is, so you are still talking about ZX. ZXX, ZXY. So you are done with ZX. So here you're starting with ZY, ZYX, ZYY. And then if you look at your first, am I too fast for you? Sorry. If you look at your second order direct partials, you will see that they are arranged on the principal diagonal. So from your very first class in matrices, maybe first or second class, you should have been taught on that type of matrices or whatever. What's the principal diagonal is. So that line that comes from the left hand side of the matrix down, to the right hand side. So this line here, this diagonal like this, that's the principal diagonal. There is another diagonal which is this, but that's not the principal diagonal. Now, if you look at the cross partials, the second order cross partials, they are off the principal diagonal. That is, they are not on the principal diagonal. All right. So there is a decision rule if you are using Hessian to optimize to check whether your functions are minimized or optimized. So the rule I spoke about here, they are just like the things that you probably be used to when trying to optimize multivariate functions. All right. So that's just it. But when we're talking about the Hessian method, so it has its own decision rule. Now, for a 2 by 2 matrix, when your answer is when your workings leads you to a 2 by 2 matrix, so the initial decision rule is that your zxx, if your zxx is greater than 0, all right, that is an indication of a minimum point. All right, so that means it is positive. Okay, so if your zxx is greater than 0, so it's an indication. You are not sure yet, it's an indication. So there is this second condition that has to hold. So your zxx multiplied by your zyy minus your zxy squared, if it is greater than, it has to be greater than 0. Now the funny thing is whether it is at minimum or maximum, this second condition has to hold, right? So what just differentiates it here is the first one, zxs is greater than 0. Now, of course, before now you should already know that when you do your second derivative and the answer is negative, the function is likely at a relative maximum, okay, at a maximum point. So, which is what is here? You do your second derivative and it is lesser than 0. That means it is negative. So your function, I'm not plotting any curve here. You did all of this is your first year, okay? So your zxs is negative, so it's showing you that your function is at a maximum, okay? Um, kind of suggesting. I'm not sure yet. Then if this one also holds, that means it confirms it that your function is at a maximum point. Here, the second derivative is greater than 0. It is a positive value, so an indication that your function is at a minimum point. And if this condition also holds, then confirmed. Yeah. So let's try out an example. So here we have, and this is easy to memorize, please. This is easy to memorize. Zx and zy is just you find like a way of finding the determinant of a matrix. This multiplied by this, that's what you have here. Zx multiplied by this minus this multiplied by this. You understand? But zxy and zyx, they are equal. So we just assume that you solve them as zxy. So it's more or less like saying zxy multiplied by zxy is giving you zxy squared. So when you find the determinant, and the determinant is greater than 0, right? So you then look at the first stuff, okay? Is it greater than 0 or lesser than 0? And that tells you what your answer should be. So here, let's start working. So we have zx. This is going to be 6x minus y minus 4, okay? then zy equals there's y here minus x, write it well, minus x, then plus 4y, then minus 7. All right, so the first other condition is that let zx and zy equal 0. So when that happens, so this becomes 6x minus y equals 4. I said in you are at a higher level, so you know how I got this one. Then for this guy, so we have minus x plus 4y equals 7. Let me name this guy like equation 1. So this guy equation 2, equation 3, equation 4, equation 5. So what you have to do now is to present the answer in a matrix form. So I'll call my matrix A. I love A a lot. So you have then you have to take note of your arrangements. X is on this column, Y is on this column, then you have the constant on the other column. Alright, so we have 6 minus 1, then this guy is minus 1, this one is 4. Alright, then we have x, y, because x is here for us, so x stops it. You should know this thing. Okay, then the constants, so you have 4, and then we have 7. All right, so in order to get a critical point, first thing is we have to look for, this is where we now start to apply, what do you call it? What did I call it the other time? Cramer's rule, right? Okay, good. So determinant of A is going to be equal to 6 multiplied by 4, that's 24. So you have 24 minus 1 times minus 1, that is 1. So our determinant of A is 23. All right, now we need to look for something else. So I'll call my matrix, my new matrix, matrix AX. So because I'm trying to look for X. So what do? I replace this column with this constant here. So I have 4. Like I said, this is Cramer's rule, so it's not a big deal. Minus 1, 4. So my determinant, my AX, is going to be 4 times 4, that's 16. 16 minus 7 times minus 1, minus 7. So 16 minus 7 is going to give us 23. Okay, so that is telling us that x, how do we find x? X is equal to determinant of AX divided by determinant of A. So we have 23 divided by 23, that's equal to 1. Alright, basic. So the next thing is AY, because we're looking for Y. So matrix AY equals, okay, now here you have to be very careful. So 6 minus 1 maintains its position here. 6 minus 1. So this side, we are now going to replace this column with what is there. So we have 4 and then we have 7. Alright, so the determinant of AY will give us 6 multiplied by 7, 42, minus 1 times 4, minus 4. So this is 46, right? So y equals determinant of AY divided by determinant of A. So we got 46 divided by 23, right? And that is equal to 2. So at the end of the day, our critical points, x, y, is equal to 1 and 2. So now we've been able to get our critical point. So is the function maximized or minimized at this critical point? So that's what we are looking for. I have to rub off this side of the board now. All right, so cool stuff. We've gotten our critical values, critical points. So the first thing is zxx. Now we go back to our original um, matrix, which is this. So here, this is our zxx, this is zxy, zyx, zyy. All right. So kind of maybe we should remind ourselves zxx, zxy, zyx, and zyy. So this is the format we're following. So if you look at it, so you then say h equal to that's how you put it. So the Hessian h equals to, so zxx is 6. All right, equal to 6, and 6 is greater than 0. So this is an indication of minimum, but we are not sure yet. We are not sure yet. It's an indication of a minimum, that the function is minimized. So the next thing that we are going to do is to find our h2. So h2 is remember what I said here. Zx multiplied by zyy. So 6 multiplied by 4, we have 24, minus this multiplied by this as a minus 1, so that's 1, equals to 23. If you look at this as well, this is greater than 0. So how are we going to you know um, write our how are we going to explain our results? So here we say that the function, this function is the Hessian. Okay, for us is that the Hessian is positive definite. Okay, so we say that the Hessian, or let me how do I write it here? Okay, yeah, that's right. The Hessian, so which is h, okay, which is this h, is a positive definite. It's positive definite, and z is minimized, where x, y equals 1, 2. Something like that. It's not a must you frame it this way, but something like that. So you can see, as I said earlier, it's a pretty simple stuff. Alright. So after this, if you have any question, you leave them in the comment section, or you ask me where you know, you can ask me. So you can hit my DM on WhatsApp if that is how we're still operating by the time you're seeing this video. Okay. So it is what it is, though. So there are, if you have any question, you can put them forth. If the stuff is not that understandable, you can rewatch the video again. So that is one of the benefits of having a YouTube class, like a video class. You can go over it again until you understandable. It's simple. So the next thing I'm going to give you now is an assignment. Now the assignment is not going to be as straightforward as this. It's an economic application, something that you've been doing before, something similar to it. Just that in this case, we are asking you to show that the function is minimized or maximized using Hessian in method. So that's just the difference. So instead of you to use the normal way, normal route that you use to just use the Hessian approach. Right, I'll write the question now. Oh, yeah. Here comes the assignment. Given you have two indirect demand functions. So given P1 as this, two goods Q1, Q2, and P2 as this, right? And a joint cost function for a non-discriminating monopolist as C equals, that means this monopolist is supplying, uh, this monopolist can choose to discriminate by supplying to markets, okay, because there are different demand curves. But here the monopolist is not discriminating. So an adjoint cost function for a non-discriminating monopolist as C equals that guy. So hey, use the Cramer's rule to get the profit maximizing quantities Q1 and Q2, and B, apply the Hessian second order. So this is where the lesson that we've learned, this is where it's going to come in. Apply the Hessian second order condition to see if profit is maximized or not. Alright, so before today, you must have been, you must have come across how to solve problems on price discrimination or not. So what you've been doing then, so do it again, repeat it here, but use something else to tell us if profit is maximized or not. So that's not about that. In the next class, we'll be talking about Hessian still, but then we'll be looking at a 3 by 3 matrix. So what are the rules and so on and so forth. See you there. Thank you for watching.